In this module, we'll be looking at potential difference in a circuit, as well as a little bit of field theory. I feel that if you don't understand the field theory, it's hard to understand actually what's happening inside of a circuit. So we'll actually talk about electric potential versus potential difference and potential energy. The word potential gets used quite a bit and in different contexts, and they're meaning different things. So we really want to have a clear understanding of what potential difference is by the end of this module here. Now, what we also want to understand is, anything that's moving has energy, okay? And the things that are moving in electric circuits are usually electrons, okay? And that the energy given to these electrons is really the potential difference. And we'll come to that in a little bit more detail. We're looking at the potential differences between 2 points on a conductor or 2 points within a field. So as I said, we'll talk a little bit about field theory, which the textbook doesn't do. So they'll be referring to conductors in the textbook, but we'll be talking a little bit about electric fields in general. We'll look at the units. So we're going to be looking at volts, understanding potential differences, joules per coulomb, and a little bit at the end there, looking at the energy, the work done by a circuit. So let's have a look at some electric fields now. So an electric field has arrows, and the arrows represent the direction a positive charge would move if placed in that specific position. So if I put a positive charge here, the other positive charge at the center of the field, or the charge that's creating the field here, okay, would repel the like charges and push it away. So the arrows represent where a positive charge will go, and that's important. See, if we have a negative charge in the middle and we have an electric field created by this negative charge, okay, the arrows are now facing towards it because this is an attraction force between the positive and negative, positive and negative forces. Now the thing with charges, I should say, the thing with field diagrams is the distance between the lines. Now this is just a model, okay, so not one line doesn't equal like 2 newtons per coulomb or anything like that, okay, it's just a model showing the strength of the field as well as the direction of the field. And how do we know the strength? Okay, here, the distance between the lines, the closer they are together, or the more lines close together, the stronger the field. And as we get further away, what we see is that the field gets weaker, and so there's a longer distance between the field lines. And that's consistent with all field diagram drawings, so that's one thing to remember. So the distance between the lines represents the strength of the field, and the arrows obviously show where, in this case, a positive charge will go. And so what we have is this idea of potential energy and potential difference. So looking here, if I had one charge, okay, and the charge was here, so that's our charge. If I left that charge and it was a positive charge, it would get moved out until this specific point, okay? Now, what we realized from previous study is we realized that the work done on a charge is equal to the force, okay, times by the displacement. And that's consistent with all of Newtonian mechanics, okay? And so what we have here, we have a force being applied at this specific point, and it's moved a certain distance, and we can call that S, okay? And now what we realize then, if we just have a quick think about it, is if the force goes up, okay, then the energy also goes up if we keep the same distance, all right? But if we have the work is equal to force times distance, if the force stays the same, then we have to move a larger distance, which would give a larger work, more work. But if we had the case, which we're going to look at now, talking about equipotential lines, as if the work stays the same, okay, and the force goes up, then the displacement goes down. This is kind of like a contour map. These lines that we're showing around here, these dotted lines, are equipotential lines. That means that a point here has the same potential energy as a point here, or same electric potential, I should say. And now I haven't spoken about what is potential energy. Well, the potential energy is the potential for the field to do work. So if I have a point in here, it has the ability, the field, to do all of this work. It's going to have more potential than a point out here, which would just start here and do this little bit of work. Okay, so if we drew some diagrams for that, okay, if the first charge started here, it would obviously be positive, and went out here, it would have a larger energy than a point charge starting here and traveling this distance. Okay, sorry, once again, excuse my diagrams with a broken hand, it's quite difficult. And now why is that different? This is a shorter distance, and if we come back to this formula, if we have a shorter distance, okay, we have less work done. And so the potential is the potential per charge, okay? And we're going to talk about some definitions soon. So these field lines represent equipotentials, which means the potential for the field is the same around there. And that means that that's joules per coulomb, okay? So it's depending on the charge. If we put a larger charge there, we're going to get a larger force. If we get a larger force, we're going to get more work done. So the amount of actual energy or potential energy is dependent on charge as well. Whereas if we just talk potential, we're just focusing on the field, okay? And what we notice, we spoke about the force, okay? The force is much weaker here than here. And we haven't looked at Coulomb's law. We'll have a look at it in a couple of slides. And what we realize is as we get further away, that the force will increase and decrease, as the inverse square law. And this is really interesting. So if we have less force, we have to travel the same, we have to travel extra distance here than here to have the same potential difference. Okay, so these lines have the same potential difference between them. They might be going up in 10 joules per coulomb. So this one here would have 50 joules per coulomb. This one here would have 40 joules per coulomb, 30 joules per coulomb, 20 joules per coulomb, and then 10 joules per coulomb. As I said, we're getting less and less potential as we come out because a point closer has more potential for the field to do work on it than a point further away. And this is the field diagram of two parallel plates. So imagine that all of these plates has negative charges along there, and this plate has positive charges. And you notice that the equipotential lines are equidistant, meaning they're the same distance. This one varies as we go out, but inside of a parallel plates, what we get, okay, is if this point gets closer to here, it gets, so we'll make this an electron. If we call that an electron, probably chose the wrong color here. So if we make that an electron here, it's going to get repelled. It's going to get pushed in the opposite direction. Remember, the lines here represent what a positive point would go. So the repulsion force is going to get less and less as we get further away from this plate. But at the same time, it's being pulled by these positive charges, so the attraction force is going to be getting stronger and stronger by the same proportion as the negative plate is getting weaker and weaker. And that's why these lines become equidistant. And here we see the difference between these. These are potential lines. Okay, once again, if I wanted to work out the potential energy of this electron, I would have to multiply it by the charge on the electron, which is the elementary charge, to get the actual potential energy. Okay, but different parts of the field, okay, will have a difference in potential, and that's called potential difference. And if points have potential difference, let's have a quick look at this. Let's choose point 1 and point 2. Okay, here's point 1, here's point 2. Now, what you'll see is the potential will increase in the opposite direction as the field lines. So as I go from here, I'm going to increase my potential as I go this direction, okay, which is the opposite to where the field lines will go, all right? Because if you're going against the force, you're giving the electric field a chance to do more work, okay? And that's a real key, especially for some of the critical thinking type questions, that the potential difference, or the potential the electric potential will be increasing in the different directions from the force. okay, from the force line. So let's have a look at these definitions and a couple of the theories. So this is the electric field around a sphere. So this is a sphere, and this is the distance to another charged particle. And what we know is, this is Coulomb's law, the force that this charged particle experiences is equal to Coulomb's constant multiplied by this charge multiplied by this charge divided by r squared. Okay, the electric field, once again, we're going to skim over this. We're not getting bogged down in this. We want to get to electric circuits in this unit, and we'll come back to a little bit more field theory in unit 3. So the difference here, the electric field strength doesn't depend on the charge itself. So this charge here that's moving, it only depends on the charge in the middle. So this has an electric field, and this was the field lines we were drawing. And so what we see is electric field is force per charge. Now that's force per charge. We're focusing in this particular module on potential difference. Okay, so let's have a look at a couple of these definitions now. So electric potential, okay, it's the potential electric field has to do work on a unit charge. Okay, so this is a unit charge, is a positive 1 charge. That's a positive 1 charge. So that's, in our case, plus 1 Coulomb, which is a massive unit. If we actually want the potential energy for something, so a potential energy rather than just a potential, what we have to do is specific to an object. So we have to multiply the potential by the other object's charge, which is kind of what we just saw with the electric field and force on a particular charge. The force depends on the charge and the field, and the potential energy depends on the field and the object charge, where the potential is just the field. Okay, the difference, which we know as the voltage, okay, is the difference between two places in a field, or in this chapter, two places in a conductor, and the amount of work 1 Coulomb of charge, once again, this unit charge, okay, would do passing between these two positions. And the work done by the field, okay, that depends on the potential difference and the specific charge on the object. So be very familiar with the difference between these, because when you're reading, it's quite often to interchange the meanings of these, and you can get quite confused. So how is all this defined? Okay, what we saw already is that force, or work done, I might just write it back up here, that the work done was equal to force times by displacement. And so in this particular case here, if we take the strength of the electric field and we multiply it by the distance, okay, what we get is force times distance over Q, because the electric field is equal to force over the charge. Okay, now force times distance, okay, maybe I should have written this one up here. In this particular case, that's force times distance. D and S are the same thing in this particular equation. They're just different terminology. And so we can substitute in now, instead of force times distance, we can put work. And we have this idea then that the voltage, or the potential difference, we can call that voltage, potential difference, it's the same thing. It's also referred to as the electromotive force, and we'll talk about that in a particular slide later on. But here, what we have is the potential difference, which is usually just written as a V and not a change in V, even though it is a difference, is the work done per unit charge. And so a volt, okay, is a joule per Coulomb, is the unit for that. Take a bit of time now and think about fundamental units and the 7 fundamental units. I want you to pause the video, okay, and I want you to derive volts in terms of fundamental units. Okay, welcome back. Hopefully you had a bit of luck there. And what we realize is 1 joule is equal to a Newton meter, okay, and 1 Newton is equal to kilograms meters per second squared. And so if I take a Newton and times it by a meter, I get a kilogram meters squared seconds to the -2. So that's joules, that's the top line. And a coulomb, we spoke about this, is an ampere second. So a volt is equal to a kilogram meters squared seconds -2 over ampere seconds. And so this one will combine with this one, and we'll get kilograms meters squared amperes to the -1 seconds to the -3. And so that's a volt, or the unit for potential difference in fundamental units. Okay, here's an extension task. What I want you to do is I want you to pause the video and go explore, how does a battery actually work? Okay, because a battery provides a potential difference, which we call, in this case, a potential difference. If a potential difference is giving energy to electrons, okay, if the potential difference gives energy to electrons, okay, we call it an electromotive force, an EMF. And so pause the video, go explore how a battery actually works, and come back and I'll give you a quick 10-second recap on how a battery works. Okay, welcome back. And so what we see here is we have a battery, and a battery has a cathode, has an anode, and in the middle it has an electrolyte. Now, different metals give up electrons at different rates. It's called the reactivity of a metal. So in this particular case, a metal is going to be used at the anode that wants to give up electrons to the cathode. And so here we show the electrons flowing around here, even though conventional current will be flowing in this direction. It's the electrons that are moving. So this metal wants to give up electrons to this metal, but it would only give up so many before this metal here would become negatively charged, okay, and then would start repelling all of the metals back. So in order for this reaction to continue, something needs to happen in the middle. And this is where you have chemicals in the middle that will react with the anode here to provide free electrons to be sent this direction. And there's the electrolyte at the cathode, okay, it will actually receive electrons, okay, and produce some waste product inside the electrolyte, or not a waste product, but some other product, okay. So the battery won't flow unless there is a chemical here to accept electrons and give up electrons from a chemical reaction at the cathode and the anode. And so if we go further, what we're going to look at is, well, how do we measure measure voltage? What we do is we have to find the difference between two different positions. And so in this case here, a battery is usually shown, or a cell, okay, shown in different ways. We'll talk about circuit diagrams talk about circuit diagrams a little bit later on in this chapter. But here what we're seeing is an anode and a cathode. And so we say that current flows around this direction. And to measure the potential difference, we need to find two different places. And that means that what we saw, I'm just going to write some notes down here, the voltage, or the potential difference, is the work per charge, okay? So the difference between here and here, okay, is the battery itself has done some work to move the electrons, okay, between this point and this point. Now, if there's a resistor in the middle, which we have here is a light bulb, okay, if we have that light bulb there, it's going to have done a little bit of extra work, okay, so there's going to be a bigger potential difference, okay, than if we're just coming around a lead. These leads are almost considered to be, it draw no electricity at all, no energy. It doesn't take any energy for the electrons to move here. Usually they're made out of copper, and copper are quite, happy to give up their electrons to move, a lot of delocalized electrons. And so what we get is a potential difference between the two, which is the energy required for an electron to get from this spot to this spot. Okay, now when I say an electron, it's not just one electron moving. Okay, so we actually have to consider all of the electrons moving in this particular case here, and that's where we're going to have to start using the term current, because current is the change in charge over the change in time. And we have a little derivation talking about energy coming up. Okay, and so let's just use this formula that we have now and have a look at an example. So calculate the electric potential energy. So we're looking at an energy now. So we have an object with a charge as well as a field that is carried by 5 coulombs of charge. So here's the object's charge and a potential difference of 10 volts. So this potential difference is in the field, and it's moving between two different places in the field or through a conductor. So just using this formula here, where you got voltages work over charge, what we want to find, okay, is the electric potential energy, which ends up being the work. Okay, so what work would be done if we moved a 5 coulomb charge through 10 volts? Okay, and so you just rearrange that equation. 10 times 5 is 50 joules. Okay, let's try one ourselves now. So the battery can provide 3,600 coulombs of charge at 12 volts. Calculate the electric potential energy that is stored in the battery. Okay, so the electric potential energy stored in the battery if it passes this much charge through this potential difference. Pause the video, try and work it out, come back for the answer. Okay, so what we saw here, it was just the same application, and we saw that the work done going through a specific potential difference is just a potential difference multiplied by the charge. So here we have 12 times by 3,600. And this is going to give us an answer with joules. And the answer we get is 43,200. And this is going to be in joules. All right, so this is the derivation I was talking to you about before. Okay, so what is a circuit? Let's have a quick look at a circuit. So a circuit, okay, means that charge is flowing. And when charge is flowing, we say it has a current, which we call I. And I is equal to the change in Q, which is charge, over the change in time. Sometimes we can just substitute that in for Q over T. So that's an important part of the derivation. So what we want to try and work out now is the work done by a circuit. Okay, we know the circuit has a potential difference. So at a battery or at a cell, okay, there's a potential difference. We call it the terminals, the cathode and the anode. And so the potential difference between them is the terminal potential, or the terminal potential difference, I should say. And so as the current goes around, okay, energy is given to the electrons and work is done. We want to work out what that work is done, okay? And it has something to do with potential difference, current, and time. Pause the video, see if you can work out, using these two equations here, how we could work out the work done by a circuit given the potential difference, current, and time. Okay, hopefully what you worked out is we could have started with work done is potential difference times charge. Now, to make this the same, we could simply say, well, we could multiply this by time and divide it by time. When we multiply by time and divide by time, it's really multiplying by 1, which is the same thing. We're not changing the value. Now, Q divided by T, okay, is current. So the work done is equal to VIT, okay, potential difference, current, time. Now, what we also know is that work done is also equal to power times by time, if we go back to Newtonian mechanics and energy conversions and so forth. So we also know that the power of a circuit is current times potential potential difference. And we'll look, once we get into Ohm's law, we can look at a couple of other derivations of that. So if you asked to find the work done by a circuit, you need to know the potential difference in the circuit, okay, the current and the time. Now we'll talk a little bit more about terminal potential differences when we do the practicals in this subject. So, okay, looking here now is a worked example. So we have a potential difference of 12 volts, which is kind of common, to generate 750 milliamps, so 10 to the power of 3, of heat for 5 minutes. Calculate the energy transferred into the water at that time. Using the equation we derived, okay, we need to use time in SI units. Current in SI units is amps, and voltage in SI units is volts. So we've been given 12 volts, 750 milliamps, 300 seconds, and we got 2.7 kilojoules. Okay, that was to be transferred into water, so that must be a hot water system. Try it yourself. Read through this question, pause the video, and come back. So what we have now is this pretty much the same situation, same application. So this time we have energy transferred, the work done is equal to the 12 volts multiplied by the 715 milliamps, which is 1.75 amps. Now, 1 amp is quite a large amount of current. It's hard for you guys to get a feel for this because you're not dealing with currents on an everyday basis. But 1 amp is quite a lot of current, and therefore we use milliamps quite often in practical situations. And 7.5 minutes, so that's going to be 7.5 multiplied by 60 to get it into seconds. And when you put all this into the calculator, you will get 9,450 joules. Okay, so as we talk through the chapter, what we've looked at is the potential difference. Okay, understand that that's the potential energy per unit charge, the potential for the field or the circuit to do work per unit charge. Okay, voltage is measured by a voltmeter, which we connect parallel in 2 different places on the circuit, and that the voltage is the work done per unit charge. Okay, the potential difference is, as we said, joules per coulomb, and is also, talking about measured by a voltmeter as well. Okay. We played around with this formula, being able to calculate different things, and especially with the energy one at the end. In a circuit, the energy charges. So have a look at the other videos, a couple of the simulations, and get familiar with the idea of potential before answering the questions at the end of the chapter, or not end of this particular module.